All right. So now, what are the topics that you want to discuss? Maybe some of the teachers could pick up those topics that have been repeatedly asked for.
Sorry, go ahead.
Also, I have sent to you an email where I listed the topics. I think you've covered some of them during your presentation on the variable selection and model selection methods, but there's still some of those which would be interesting. So maybe you can go through the first two of these.
Yeah, maybe you could just tell what are the questions, so I don't need to.
Okay, so one of the questions which arose many times was about the flexibility of including the spatial, temporal, or well, more flexible spatial terms rather than we have now. Or it's maybe even better to call them more flexible autocorrelative terms or Gaussian process prior terms. So it's clear that there is a demand for three-dimensional structures where 2 dimensions are different from the third one, either in the spatial temporal context or in context of marine modeling, where the depth is principally different from xy coordinates. So any feedback from you on this aspect?
Yes, this is a very important topic and something that we have realized ourselves in the development needs of HMSC. And now, if I share one slide that I have shown before that relates to this, to once again go through what is the issue. The issue is that when we implement these spatial or temporal or whatever site loadings, we estimate the spatial scale parameter alpha. And in one-dimensional space, for example, time, this alpha is in the units of time. That's okay. In two-dimensional space, like x and y coordinates, like we often have with terrestrial data, alpha is the distance between the sites in that two-dimensional space, so that's good as well. But for example, in this case of a marine environment, it is truly a three-dimensional space. We have x, y, and z coordinates, where z coordinate is the depth of the water where you took the sample. But in that case, it's not so nice to have a single alpha parameter there, because you don't expect that the spatial scale of autocorrelation is the same in the x-y directions as in the z direction. Or if we have spatio-temporal data, that is three-dimensional data as well. If we have two-dimensional space, we have x and y coordinates. They are in terms of kilometers, for example, and then we have the time coordinate, which is maybe in the unit of years. So it's quite unnatural to combine these units into one scale parameter, for example, to decide that 1 year is the same as 10 kilometers, which you would need to do to model this now as a three-dimensional variable. So we have not implemented yet, for example, these spatial-temporal covariance structures, or these kind of covariance structures where you could say that you have three-dimensional space, but the spatial scale should be different for these two coordinates than this last one, which is the time coordinate. What we have implemented is that you can have an arbitrary number of these random effects. So you can plug in one for space and one for time, but then you are kind of estimating the main effects of space and time, but not the kind of the interaction between these. So that then you basically assume that whatever is the spatial, let me try to illustrate this again with the slide. This slide. So for example, is assume that this spatial shape here remains fixed, that it's always the London area that's highest and this area which is the lowest. But then over the year, just the level changes. So this would be kind of having the space and time as main effects. But then if you want that this spatial pattern also varies across the years, then you have a spatial temporal random effect. And that we haven't yet implemented. And the main reason why we haven't implemented it yet is that Gleb has been so busy with all the other things that this is in his pipeline somewhere, I don't know, number 7 waiting to be done. Or what do you say, Gleb?
Well, I would say that it would be really easy to implement them in a manner which is going to be cubically scaling. So it's going to be scaling as the typical, well, scalability of Gaussian processes. But perhaps such systems, especially special temporal systems, they require something more smarter than that. And if you recall, we had kind of initiated some type of research on that around like 3 years ago, but then it gradually didn't receive kind of maybe enough attention or enough progress, or maybe we didn't have enough data at that moment for kind of to proceed with such type of research properly. So there is definitely certain amount of work has to be done in order to make these things nicely scalable and practically efficient for answering practical questions.
Yeah, I think this is the case that there's no problem for us writing right now an equation for those spatiotemporal covariance structures, and others have done it in many times. There is no problem writing down how the MCMC sampling could be done, but what is difficult is to write down the equation of how it's done computationally efficiently for big data and then to implement that. And I don't think this is any super amazing challenge compared to the other challenges that, for example, Gleb has overcome, but it just needs to be done. And just to remember a bit the history, when I said that, hey, Gleb, why don't you implement spatiotemporal structures, you started doing that, but then you figured out that, hey, it's better that we first focus on spatial structures, because when we talk about spatiotemporal data, we always have a lot of sample units, so then it's important to do things computationally in an efficient manner. And then you first did this, how to do big spatial data in a better way, and now this would be a starting point for spatiotemporal structures.
Okay, so I think it's that's enough for the first point which I wanted to raise. So the second point would be about inclusion of random slopes into an HMSC model. So currently, obviously, HMSC has random slopes with respect to the species identities. So we have different slope with respect to the fixed effects for each species. But at the same time, if we think of that we try to model only univariate, like only single species at a time with HMSC model, we don't have a neat mechanism to include the random slopes with respect to different different units on some random factor levels. So imagine like we have global community, modeling community all over the world, and then we are trying to say that perhaps on different continents, our slopes for the linear part of the regression, linear part, they can be different, but they come from some joint normal distribution. So I would say that perhaps this capacity is somehow missing from current implementation of HMC. We had some conversation about that. Formally, definition of such model would be pretty resembling the definition of model which you currently use for covariate dependent species associations. But whether there is exact match between these two wasn't very clear at that moment, and we didn't we didn't dig very deep into the topic at that moment during the breakout session.
Yeah, that's a very good point. And as you said already, it relates a bit to this issue of covariate dependent associations. So here we have this Gleb's first author paper from 2017, which asked how joint species distribution models can be used to evaluate how these species association matrices depend on the environmental context. So that here the omega matrix is modeled as a function of some environmental covariates, some measured covariates, by assuming that those species loadings, those lambdas, depend linearly on some environmental covariates, and then that generates species association matrices that vary according to those environmental covariates. And the similar thing could be done to just assume that they vary over space or time that we haven't done. We have done this over environmental covariates. So this is what you can do if you bring in X data for the random effects. This is a pretty complicated model. We didn't illustrate it. It needs a lot of data to be fitted well, but it's implemented. And now actually I can confess that when I was writing this chapter about, like a section about this method to the HMSC book, I started writing by explaining that this corresponds to the random intercept slope model. Okay, but once I was progressing with the equations, I realized that, well, it doesn't exactly correspond to it. There are some similarities, but because we have kind of a product between the fixed effect and the random effect in a sense. So there is some similarity, but it's not the same model. So you are absolutely correct that we haven't implemented this typical random intercept slope model, and that's something that we could think about in the future. It's a bit, I haven't gone through this in detail, like with pen and paper or tried any simulation, so it's not very clear to me yet, like what would be then the correspondence between that and then these covariate dependent species associations, because I guess like that model would also produce some association matrices among the species that could vary with some covariates, but this is something that we should have a look at whenever, you know, there is the bright person who has the time and motivation to do this. So it's a very relevant question of how this could be done. I don't know if the other joint species distribution models that there are actually do this. If yes, maybe somebody could comment in the chat so then people know which package to use for that purpose.
Well, that was basically 2 points which I wanted to raise in this discussion. So now I give the stage to other members of HMSC team.
Yes, I don't know, for example, Nerea, are you here still? I think you also had in an email some IDs. Maybe she is not anymore, at least not right now. So then maybe I can go to a couple of things that I have on my list, so which are partly like relatively simple, like questions that I received that I couldn't fully answer. So I wanted to bring them here so that hopefully my collaborators can give a better answer. So one was that so far in all the cases we have been looking at, we are, for example, looking at presence absence data, and we set a probit link function for all the species. But in HMSC, it's so that in principle, you could have like 10 species, 5 of which are presence absence, and 5 of which have abundances. You can have like 5 response variables with a probit link and 5 with a identity link, a Gaussian model. I think like in principle, that's straightforward to set up those models and so on. Then it wasn't exactly so clear, like what does in that case, like the residual associations means? Are they somehow the correlation on the link scale?
Yes, you can indeed define the distribution not simply as probit or normal, but it can be a vector, so that there is a different distribution for every column of the Y matrix. And now, what are the associations? The associations are always at the scale of the linear predictor. Like even if you fit the probit model, then the associations are actually defined at the scale of the linear predictor. So whatever distributions you do have, a combination of them, all models do have a linear predictor, and so technically then the associations are measured at that level.
Yeah, so that then a positive association could mean that, for example, at sampling units where one species is more likely to be present, another species could be more abundant.
Exactly, that would be the interpretation in that case.
I think that was Bram that was bringing this question. So I hope that answered it for you. And we have a couple of things that there have been like calls for like demonstrating particular things in R. now, since we have only 45 minutes left, I don't think we will go to R to demonstrate them, but they include, for example, how to compute the posterior probability for a difference between categorical levels. Like, let's say if you have treatment in your model and you want to know what is the support that the mean species richness in the treatment is different, or things like that. I suggest that people that want to do that and don't figure it out on themselves, then please email us and we will help you with that. And another thing that people wanted to do was to compute like this environmental covariances. So in HMSC, we always look at these omega matrices, which is like often the correlations, but can also be like the covariances on the kind of the random part of the model. But of course, there is also some covariance among species distributions, for example, that is due to the shared response of the environment. And this is somehow very like straightforward to compute because it depends only on like the regression coefficients and the covariance structure of the predictors. We haven't like implemented that. So again, if someone needs to do that, please contact us. And I think in that case, that's also something we want to add to the package, that right now we can compute. I think there is a function called compute associations, and in that one there could be a choice, get like the environmental associations.
Yeah, that would be indeed trivial to implement. Just compute associations would do it also for the fixed effects. That wouldn't be difficult at all. It just needs to be done. And it's, yeah. I wanted to say one thing about this having different response variables in the same model. So let me again share my screen. I wanted to show this recent Oikos paper by Sonja Saine, who, by the way, is possibly here in the audience, and others, where I want to show one figure of this one. So now this is an association plot that resulted from some HMSC analyses. You see that we have here, this is fungal data, we have fruit body data and DNA data. So in the same model, we included fruit body data and DNA data for the same species. And then we did the hurdle model for both of these. So we have the occurrence and abundance conditional on presence, again for these same species. For fruit body data, we didn't have the abundance data for all species because they were not simply measured, but many of the species are 4 times in 4 columns of the same HMSC model. So there are fruit body occurrence, DNA occurrence, fruit body abundance conditional on presence, DNA abundance conditional as presence measured in various ways. And now it can indeed be very interesting to look at these associations between these different types of data. For example, is it so that the DNA that we got from the inside this dead wood, is it so that it was especially abundant when there was a fruit body present? And these kind of associations are now seen. So it's always possible to fit, for example, the hurdle model in one model, if you like. You can combine the data so that you just have every species twice in the Y matrix. That's an alternative of doing it separately. The reason why we often do it separately is that these 2 models are statistically independent of each other, and then there is kind of no need of putting them to the same model. But if you have these different types of data for the same species, like here Sonja had, then it's nice to combine them.
Show the whole PDF because they don't see the whole PDF.
So Neda said that you don't see the whole PDF.
I think it was the figure that people wanted to see.
Sorry, what people wanted to see?
People wanted to see this figure that you were just showing half of.
Ah, I was showing half of the figure. Okay, sorry for that. So this is basically the figure. So it's a species times species association matrix where we have first ordered the species or the data types, so that we have fruit body data first, then DNA data, and then within each first the occurrences and then the abundances, and then within each of these we have ordered the species in a way to illustrate these patterns.
So just one quick follow-up question, because you said that this as an option to fitting 2 separate models, we could put like the presence and the abundance conditional are present in the same model. So wouldn't one difference there be that then you get kind of the joint posterior, so that you can get, if you multiply them together, you could get like the correct credible interval?
Yes, except that, you know, maybe Gleb corrects me if I'm wrong, but in my understanding or reasoning, these two data types, presence absence and abundance conditional on presence, they are statistically independent of each other. So in that sense, you would expect the posteriors to be fully kind of that there is no joint structure between these two. Of course, some joint structure can be kind of forced by the prior part, this hierarchical prior of HMSC, which is trying to find some common means and variance covariance structures. But then I would say that that's more kind of an artifact than an ecological result, because the two data types are really statistically independent of each other. Or what do you say, Gleb?
So can you repeat last sentence, because I'm not sure whether I kind of heard what you were talking about.
That if we talk about the hurdle model, that you split the data to presence absence and then abundance conditional on presence. Now,
yeah, well, by default, those two would be independent. But if you start including some components like phylogeny, that can impose some dependencies. And it's actually not very clear how to include phylogeny to such model, at least for me at this moment. I mean, you can kind of assume that like your beta variables, beta covariates for these two outcomes. I mean, four outcomes in your case. So twice the fruit body related and twice the DNA related outcomes. So you can actually force them to be equal just by setting that like your phylogeny for this kind of pseudo species are exactly the same. Phylogenic similarity for them exactly the same.
Yeah, so that's basically what I tried to say, that these two components of the model, presence absence and abundance conditional on presence, they are at the level of the likelihood of the data, they are independent. But then the prior structure of HMSC, which includes the relationship to traits and covariates, that can imply some dependency, so that the posteriors can kind of inform each other, that is somehow you can borrow information from the other data type. But typically, at least personally, I wouldn't like to do that. I would maybe like to fit them as two independent models, because then I can really compare the results and see if they tell a coherent story or if they give different results without having any risk that, for example, they give the same answers just because there is a common prior that is somehow kind of inducing it.
Yeah, well, I agree with you, but well, I would say that like it still makes sense to fit them within the same model, so that you just need to be quite careful about your priors and what type of assumptions those priors impose.
Exactly.
I would believe that there is a way to do it which would be ecologically meaningful and at the same statistically coherent.
Yeah, and sometimes we have done it like in this case, we have included both types of data to the same model. And I also would like to say that this Gleb's answer was very, very general, that you typically answer my questions that, yes, I agree, but.
So both of you, since we now have you here and we are talking about the hurdle model, and maybe we could just briefly mention now that, as we've been saying to many in the breakout groups and so on, in this case, many of the data where we have fitted the hurdle model, these are these kind of zero inflated count data, where we would like, intuitively, we would go for this like log normal Poisson implementation, but then at least I've been saying that unfortunately what happens is that often we get like poor mixing properties and so on. But could Gleb, for example, comment on, is that something that we have some hope on improving in the future, or is it like we should stick to the hurdle models for now?
What do you mean? Whether there is a hope, whether we would improve the log normal Poisson?
Somehow, yes.
Because I would not say that like even if we have a perfect log normal Poisson, I mean perfectly fast, so I would say equally fast as the model with log normal transformation. I would say even in that case, it may be that like you would need to sometimes to select the log normal transformation, and in other cases you select the Poisson for the positive values. So you don't completely replace the hurdle model with that. You still need the model for the presence absence, and on top of that, you need the model for the abundance. It just like depends what model for the abundance you use. Either for the log transformed data, or you use the true log normally distributed Poisson, sorry, log normally over dispersed Poisson model for the positive integers. But indeed, like, I mean, indeed, maybe answering your question more specifically, we are specifically aiming at improving our sampling efficiency manifolds.
Good. That's what everyone wanted to hear.
Yeah,
Me as well. Me as
the
well.
Poisson at the log normal Poisson, they work in theory in the sense that if you generate simulated data from those and you estimate the parameters back, they work, they give the right inference. But then in practice, they often converge very, very badly. And maybe that's one reason why we then have taken the quick and dirty approach to do a hurdle model where abundance is a log normal linear model.
So maybe now is the time. Now we have kind of been answering many of these questions that we've been collecting during the course, but it seems like maybe there could be people now in the audience sitting and having burning question that they would like to get an answer to. So could people please like write in the chat now if they have any particularly important questions or any question for that sake?
Okay, Doug is asking how to do conditional predictions. And so there is this YC equals something in the predict HMSC. So when you do the unconditional predictions and you don't give this YC, then it just predicts the whole Y matrix. But then you can give to HMSC the part of the matrix that you want to condition on. So the baseline prediction where you don't condition anything, you get if you say that YC is the same direction as the matrix that you are trying to predict, but all the entries are NAs, missing values. Then you don't condition on anything, and this is exactly the same as not including YC at all. But if you, for example, let's say you do a presence absence model, you have a YC where all the other elements are NA, but then for sampling unit 5, for species 2, you put the 1. Then you are making a conditional prediction where you predict everything else conditional on that's being present in that site. So now you can have an arbitrary pattern in YC of the data that you condition on, which are the numbers that you put there, for example, 1s and 0s if you have a presence absence model, and then NAs, which are actually the values that you are predicting. Now, when you make this prediction, you will get the Y matrix, which is of the same dimension of this YC, the thing that you try to predict, where those values that you conditioned on, they will exactly have those values that you conditioned on. You force them to take those values, and then the rest is predicted conditional on those. Yes, so Doug is saying it's the Y matrix with NAs in all the elements that we want to predict, indeed, yes, if you do unconditional prediction. So let's have a couple of minutes like this, that whoever wants to ask whatever, you put into chat and we answer. Are there any issues with fitting the log normal model on zero inflated data other than potential issues with chain mixing? If it converges, are there still risks that the model assumptions are not met? This is actually a good question, more general question. The fact that you achieve HMSC convergence doesn't mean that the model is like a well specified and that it kind of fits with the assumptions of your data. Because at least theoretically, if you just run the chains long enough, you can always achieve HMSC convergence more or less. And now if you misspecify the model badly, most likely the HMSC convergence is worse, but still it doesn't say the fact that you achieve it or not. It's a completely other topic than whether the model is actually something that fits nicely with your data. You know, if you fit the linear model, univariate linear model with the LM function, then you can always fit it whatever typically you always get some estimate whatever are the data about. So it's a second step where you need to examine if the residual variation is normally distributed and homoscedastic and all of that. So we haven't discussed a lot about how to check this kind of model assumptions. There is an example in the book how you check with HMSC whether your residuals are normally distributed and maybe homoscedastic. So you can of course do all of that. And so now, yes, there can be issues fitting the log normal model on zero inflated data if you use the log normal model for pandas conditional presence. Maybe your residuals are not sufficiently normally distributed, and then that will be a problem. So that's something that you should worry about. And let's say that if, for example, your count data are such that you have values 0, 1, 2, 3, and that's all, then it sounds a bit dubious to fit the log normal model for abundance conditional presence. Then probably you really want to fit the Poisson kind of a model because you have such discrete nature of the data. But then quite often, for example, with sequencing data where you have like 1 million sequences per sample in total, and each species is represented by quite a good amount of sequences, I think it's quite often okay to use something like the log transformed relative sequence abundances and do a linear model with that, or the log transform sequence numbers if you control for sequencing depth by putting log sequencing depth as a covariate. Theoretically, it's not a beautiful model because it does not account for the fact that the sequence proportions they sum to 1. So you would like to have a multinomial model on top of this kind of a construction, but in practice, I think often the log linear model works well with that. And I mean, people are often worried about these artifacts that you are forcing some positive or negative associations because you don't account for the multinomial nature of the data. This is very true, at least theoretically. I mean, it's easy to construct a case where this is a problem, but in practice, if you have a case where you have a species-rich community and a lot of species are relatively abundant, so that it's not so that there is one species or the other species present, which would create this kind of a very strong negative correlation that you should account for. So then, at least in the examples that I've done, I haven't seen these kind of spurious correlations appearing to the extent that I would be especially worried about those. I'm worried about those, but usually there are other parts of the model that I'm more worried about. For example, whether the study design is accounted for by appropriate random effects.
Also, may I ask you one question from the chat, which also appeared in my breakout group, and I think I promised to ask it to you, but I kind of forgot to put it on that notes. So in case when we do the variance partitioning and there is linearity in our predictors, what happens with in that case? How is it actually partitioned?
Yes, that's a good point. Let me go back to the book to show how it's done at the level of the equation, while I'll try to give you a verbal explanation. So here we have the variance partitioning section, and so the variance partitioning is basically just based on looking at the variance in the linear at level of the linear predictor, and basically what pops out in this kind of a simple calculation are the squares of the betas times the variances of the individual predictors plus twice each pair of betas and then the covariance between these different environmental predictors. So now if you're, and basically we kind of ignore this part. We just artificially put this part to 0 when we do the variance partitioning, so that we only focus on these variances, except that something else we do that I will explain later, but we more or less just ignore these covariances. So now if your predictors are orthogonal, then this is okay, then they will not contribute anything. But if they are not orthogonal, then they do contribute with the help of these covariances. And you can calculate this, of course, yourself and then see what are the covariances between all of the covariates and multiply them by these betas. The reason why we haven't included them in the variance partitioning plot is that this is simply quite tricky to illustrate. How do you illustrate all of these covariances? And of course, one approach would be that you just sum all of them up and then add that to the bar. But then there is this issue that this can be, I mean, these are always positive, these variances, but this can be negative or positive. And so they can total in a negative value, or they can cancel each other. You can have strong covariances, but then the sum of everything is zero because they cancel each other. So I would really like to plot this for every pair of covariates. So it's easy to do that, illustrate that for a single species, that you have a covariates times covariates matrix, which illustrates how much each pair contributes as variance or covariance. But then it's not so easy to make this kind of a plot maybe at the community level for all species, and that's why we haven't illustrated it. But now, what we have done to go a bit to this direction is that you can group the covariates in any way that you like. So this is the actual equation that has been implemented. So you can group your covariates when you do variance partitioning plot by placing several covariates to the same, several predictors to the same categories. Now, very trivially, if you have a categorical predictor, you want to group all the dummy variables related to that into one. Okay, so that's like what is the variance explained by that single categorical variable with all the levels. It has several betas, but those you definitely want to combine. And in the same way, you often want to combine first and second order terms of some continuous covariates. And now, I think thanks to Jari's efforts, HMSC automatically groups some obvious cases like these categorical variables, but then you can define whatever grouping you like. You can group all the climatic variables into one and all the habitat variables into one group, so that in the variance partitioning, it only tells you the variance proportions in terms of these groups of variables. And now, if you do that, it does account for within group covariances. It does account for with covariances between the variables that you have put to the same group for the variance partitioning, because that's it. They are easy to calculate and to account for, but then it ignores these between group covariances from the variance partitioning. So in the variance partitioning, the kind of the amount of explained variation is kind of correct, but then within that bar, things are a little bit shaky in the sense that these covariances are simply dropped out. And this is also one of the many reasons why it's nice if your predictors are more or less orthogonal, because then this is no problem, but then otherwise it can be a problem. And if you worry about that, then you just calculate these covariances yourself. It's not difficult to do, and see how they turn out to be.
So we had a couple of questions here where people are a little bit worried about the complexity of HMSC in the context of estimating relatively or analyzing relatively small data sets. So let's say in general, like in any statistical analysis, of course, the sample size will detect our power and so on. But is there like anything particular about the complexity of HMSC that should make us like extra cautious when analyzing smallish data sets?
Well, maybe Gleb can again correct me if I'm wrong, but I would say that first, if we ignore the random effects part, if we are just estimating the betas, then HMSC is not any worse than doing like a univariate models for each of the species. So that if you would think that you do corresponding univariate models and you only have these 15 data points of presence absences, that's a major problem for fitting usually univariate models. I would say that HMSC does not do any worse than that in terms of having small data. It typically does better because it's able to borrow information from the other species. Okay, but then when we come to these random effects and these species association matrices, then of course there is this issue that, you know, if you have a small number of sampling units but a large number of species, so sometimes I have seen data sets with, let's say, 20 sampling units, for example 20 DNA barcoding samples, and then 1000 OTUs. So then it's of course very tricky to estimate those species association matrices, because you are basically trying to estimate 1 million parameters from 20 data points. So then you definitely want to do this kind of a dimensional reduction that we have talked about, but still it's quite shaky to make inference about 1 million parameters if you have 20 data points.
Yeah, so maybe one thing I can maybe add to that is that, like, one thing that I think is nice with this implementation of HMSC is that if you have a relatively small data set, then what will happen is you will get your parameter estimates, but of course generally your uncertainty will be very large. So for example, typically there will be few variables that have high posterior support and so on. That means that of course it's kind of explicit that you know that it's uncertain here, and of course in this case the reason for that would be partly that the sample size is small. And then we have like the opposite question. What now if I want to, for example, if I was sending my samplers all the way around the world and getting like millions of Malaise trap samples from everywhere, and now I want to fit a global spatially explicit model with temporal structure. Are there any problems with that?
Gleb, do you want to answer that?
Well, maybe I would just like kind of to know that you have to be careful with the spatial structure which you include to your spatial random effects if you want to have that one, and perhaps you want to have that one, because well, not all spatial covariance functions are compatible with the distances on the sphere, the distances on the globe more specifically. So this is one of potential pitfall which you can fall into. But otherwise than that, well, I mean, interpretation of such model could be tricky because it kind of assumes that like the process which is described by the model is homogeneous all over the globe, and it's really easy to like it's really highly possible that this assumption doesn't hold. So these are like the pitfalls from the statistical side. Maybe you can continue on the pitfalls from the logical interpretation also.
What about computational constraints, Gleb, with massive data?
Well, I mean, there was no notion of massive data so far. So like if you have 10 places all over the world, it's not more difficult than 10 places all over Finland. So it really depends on the scales and exact numbers.
So what are the biggest numbers you've worked with so far?
Like our biggest spatial examples are constrained to like, I think 30,000 train locations and around like half a thousand species simultaneously. But then I would believe that also have done more numerous species communities, but not in sense of number of sampling units.
Yeah, what I'm showing here is this big spatial data paper by Gleb and others, which indeed shows how the model was fitted, for example, for more than 600 species with those more than 20,000 sampling units. And then I think it was Harry Wells who was asking, can I show how to check the assumptions about residual normality and all of that? So I just showed this one figure from the book where we go through the linear model, and these figures are not generated by HMSC. This comes out just when you fit the linear model with the standard package and then look at the residual variation and the homoscedasticity of residuals, and then you wonder if these are good enough. I can tell that these are good enough because these are based on simulated model that simulated exactly from the from the linear model so that these satisfy the assumptions as well as they can, kind of theoretically and in that sense. But then how to do this in HMSC? If you want to check this, you can do exactly the same thing. Here we have the same plots generated with HMSC. Here we look at the residual histogram and the homoscedasticity of the residuals, and this plot looks basically identical to the one that you get from the linear model. And also the way that you construct these plots is pretty much the same. This is how you do it with linear model. I mean, you can also call plot the linear model and then it does it for you, but you can do that by extracting for example, the standardized residuals and looking at their histogram and plotting them with respect to model predictions. Now you can do exactly the same thing with HMSC as shown here by doing the predictions, taking maybe posterior mean predictions. They kind of correspond to maximum likelihood estimates in a sense, the maximum the mean posterior estimates. And then you can calculate the residuals, plot the distribution of the residuals, and plot them with respect to the predictions. So then you get basically the same plot. So this can be done, but then note that in a joint species distribution model, you have a lot of species for which you can check these kind of assumptions. Maybe some satisfy them, some deviate from this. And then you have also other assumptions made. For example, we assume that these species-specific beta parameters follow a multivariate normal distribution modified by the trace and phylogeny. So that's another thing that you might want to check. So if you want to check all the model assumptions, which would be nice, of course, to do, there is actually quite a lot of this kind of checking to be done. Hey there, this has been a very nice discussion, and I'm sure we have still more questions popping up, and we will try to compile some of these to kind of frequently asked questions and answer them later, for example, in the web page. But because time is really running and we should be finishing the whole course in 15 minutes from now, I propose that we now stop this, have a 5-minute break, come back 10 minutes before the next full hour, and then have the final session for those 10 minutes, basically closing the course. So see you again in 5 minutes.